Should be one more person. Okay, so it's 8:20, so I'm going to go ahead and get started. A few brief announcements here at the beginning, and then we'll dive right in to class. So everybody should have noticed that I posted your graded quiz on Blackboard, okay? If you haven't noticed that, you'll see it there, okay? I posted it this morning. And I've also posted in that same folder in Blackboard where you took the quiz, my solution. So what I recommend you do with every quiz and every exam is take a few minutes once you get your graded work back and compare what you did to the solution. And focus on the things that you missed and try to have a moment where you go, oh. Because to be honest, we learn most when we make mistakes and then learn what was wrong about what we did, right? Those just tend to stick more, okay? Hi. So you can check your graded quiz and then you can check my solution. And if at any point you have a question about the solution and why it was done a certain way, you can just reach out to me, okay? I have, of course, as I've posted on the syllabus, official office hours, just to remind you. They are Tuesday morning, 9 to 11, Wednesday and Thursday afternoon, each day, 2 to 4, and other times by arrangement. Again, you can just reach out via email and we can set up a time. And when you come to my office, it means you go to Blackboard Collaborate. And that's where we meet up, okay? Okay, just a little bit of request on my part. When you upload your quiz next time, there'll be another one this week on Friday. I do ask that you upload a PDF file, a single PDF file. Okay, not multiple files, but a single one. And what I recommend you do is once you upload it, I think there's a way you can view it yourself. So please make sure that you view it and that you're not sending me an image that's sideways or even upside down, okay? It should just load in the screen so that anybody could just read it. That's what you want to be uploading, okay? If you don't know about it, there are a number of apps that you can put on your phone, like Cam Scanner, which just lets you take a photograph of, if you've got multiple pages, of each page one by one, lets you view them, even crop them if there are parts you don't want to show, and then save it as a PDF. And it'll save it as a single PDF document, even if it's actually multiple pages. And then that's what you would upload. Okay, so that's kind of the process we want to be using. Like I said, we'll have another quiz on Friday, and it'll be the same process. More short term, next thing due is homework tonight. Remember, the tutor is available from 6 to 8 this evening. Dave is available. And remember the link that I sent you a while ago via email, right? The one for Monday night Google Meet. Okay. Okay, of course, lab is this week again. Remember, experiment 2 is what you want to read before you come into lab. And you also want to look over that section on conducting and reporting on experiments, pages 7 through 14. You will need that content for this week's lab. Okay. All right, now, today is all about more practice with vectors. And the main focus today, well, part of the main focus is the 2 key learning objectives that I mentioned on Friday in class that are probably the most important 2 for the whole class. Those are, given what's called the magnitude and direction of a vector, calculate for us what are called its scalar components. And conversely, given the scalar components of a vector, calculate its magnitude and direction. Okay. Question here? Oh, sure, absolutely. So what I want to start with is just a little bit of practice before we do a Wiley Plus type example problem. Drawing what you might call the component triangle. Given a vector, make a triangle with that vector and its 2 components. And we need to be able to draw that component triangle correctly. So I want to practice with some scenarios. Let me show you some pictures. In these scenarios, we have 6 vectors. They're all labeled little a arrow, but they're 6 vectors, all in their own XY coordinate system. All right, and they've been labeled going across the screen here. And along with the vectors, there are supposedly the X and Y scalar components drawn as well. Here's our task, case by case, going down the line. Given the actual vector, remember how your book draws an actual vector versus its components? They draw an arrow with an open tip on the end, like you see right there. That's the actual vector they're telling you in this first part. Question then, let's just look at this first picture. If that's the vector we're given, and here are the 2 claimed scalar components, X component and Y component, is that picture correct? Let you think about it a minute. Okay. Does everybody come to their own conclusion as to whether that picture is correct? All right, so now, does anybody want to volunteer to tell us if they think the picture is correct or incorrect? Yeah. Incorrect? Okay. Can you tell us what makes you, what do you think is wrong about it? Okay, so that's an interesting question. Must they be drawn head to tail? It's true, that's the way I will always draw them myself. But that's an interesting question or interesting point. Must the X and Y components be drawn head to tail?
I was going to say that if you actually took the vector and drew it from the origin, it still have the same code. So it would be correct.
Okay, you're telling me how to make a correct one. Okay.
No, I was saying if you're trying to look at it from the origin, it would still have the same scalar components. So it is correct.
Oh, okay. Sorry, I misunderstood what you were saying. Let's draw the axes. I like to put little arrows on my axes like that. So do you want me to redraw it? Are you saying you want me to draw this? Shift it over so that its tail is at the origin?
Yeah.
Okay.
Oh.
You can do that. You are allowed, by the way, folks, to shift a vector arrow anywhere you want. Just don't change its length or its tilt. Okay? So you can draw it like that if you want. But then there, the way they've drawn, you got to look carefully at the picture. I know you got to look carefully. See the arrowhead on AX and the arrowhead on AY. I agree that it's not correct. Gesundheit.
The scalar components have to be head to tail, and they aren't.
That's the point I was asking here. Do they have to be drawn head to tail?
No.
Okay, and somebody in my ear just said no. The components do not have to be drawn head to tail. Do you have something you want to add? Right, okay. All right. So here's the way I like to think about it. If I'm given a vector, you can draw it here like this if you want. This is the same vector as drawn there. Let's be clear about that. All I did was shift it over so that its tail was at the origin. You are allowed to do that. You have not changed the vector as long as you don't change the length of the arrow or the angle it's tilting at. Okay? Now, I look at that and I say, hey, it points to the right and down. Would everybody agree with that? It points to the right and down. So its components, there must be one to the right and one down. That's the only thing that would be allowed, right? If the vector itself points to the right and down, then there must be one component to the right and one component down. It's that simple. Now look at these arrows. One's right and one's wrong. Which one's wrong? AX. It points to the left, doesn't it? And yes, you have to draw arrowheads on those scalar components too, but notice they're regular arrowheads. So what are all the various correct ways to draw AX and AY? Because that picture is not correct. Well, you got to have one component to the right, like this. That would be AX, and one component down. That would be AY. Note the little arrowheads. Note how they're labeled. And yes, the way I draw them, the two components are head to tail. But it's an interesting question whether they have to be drawn that way. We'll come to another one in a minute, okay? Okay, let's look at the next one though for more practice. Look at picture B. Here's the vector you're given. Here are the components. Look, I'll show if you can't see very well. AX, arrowhead points to the left. AY, arrowhead points down. Is that vector correct, or picture correct? Correct. Yes? This vector, I don't care that they drew it down here. You can imagine sliding it up so the tail's at the origin. That vector points to the left and up. So there must be one component to the left and one component up. There's no other way about it. I do have a component to the left, don't I? But I don't have the up part right. AY is the incorrect one. Does everybody see that? It's very important, by the way, that you draw the arrowheads on the component parts. Otherwise, nobody knows whether you're saying the correct direction for it. Let's look at picture C. There's the vector A. See it? AX points to the left, AY points down. Is that picture correct? Yes, that's correct. The vector itself, just look at it, points to the left and down, right? So there must be one component to the left and one component down. AX is to the left and AY is down. Perfect. Couldn't have drawn it better myself. Let's go to D. There's the vector A. Actually, it's the same as in C, isn't it? Now there are the components, AY and AX. Is that one correct? Yeah, it's okay. One component's down, one component's to the left. Yes? That brings up an interesting point. For a given vector, you could either draw C or D, couldn't you? For the components? And they are equivalent, okay? That picture and that picture, to a physicist or a mathematician or an engineer, those two pictures are exactly equivalent. E. Love. They're both wrong, both components you're saying. Well, there's the vector. And yes, they drew it down here, but if you want, you can pretend sliding it so that its tail's at the origin if you want. However you slide it, it points to the right and up, yes? So it must have one component to the right and one component up. Neither component is correct, is it? So that one's wrong on both counts. What about F? It's an interesting looking one. I don't tend to draw it that way, but is it correct? Yeah, it is. Because the vector itself, in this case, points to the left and down, so there must be one component to the left and one component down, to the left and down. So you'll sometimes see the components drawn that way. And that one is also equivalent then to C and D. Okay? I would tend to, myself, personally, I tend to draw either C or D. But F is perfectly acceptable. So we must be able to recognize these drawings with components. We must be able to make them ourselves correctly, okay? And the reason we're harping on this is because many, many, many quantities in physics are vectors. And the other reason it's really important to be able to draw these pictures is a little bit later on, not too far away in time, we're going to be working with coordinate systems X and Y that aren't in that normal orientation, but are tilted. And we still have to be able to draw the vector triangle, okay? So these drawings must be very familiar to us, is the point. All right, that's just some basic practice with making sure we can draw the correct picture of, given a vector, how do I draw the component triangle? Now I want to do a Wiley Plus problem that's going to focus on figuring out the components of a vector from wording in a problem, and then finding its magnitude and direction. All right, so here comes the situation. We're going to play a game of chess. Well, we're going to talk about a game of chess. To pass the time, two people are playing a game of chess. The figure below is a drawing of a standard chessboard, and an XY coordinate system has been included. Note that the origin of the coordinate system is at the lower left corner of the board, okay? Each square has edge length L, as the drawing is implying, okay? In two moves, one of the players has taken a piece, the queen, from the square labeled E4. This is just a kind of way to note the various squares. E4 started right there and ended up at square C7, C7. If you look carefully, there's a blue arrow there that represents the displacement for that chess piece. And I happen to pick the label capital A arrow for that displacement. All right? All right. I don't care about that last sentence, right? That's filler, just to kind of try to distract you. Here's the actual question. What's the magnitude of the queen's displacement for these two moves in terms of the distance L? And then what is the direction theta of the displacement measured from the plus X axis, okay? We've got a sketch, but I'm going to make my own version, okay? I think you can help me too. We're shown the arrow representing the displacement. It's the blue arrow right there. Note the way this picture is drawn, the displacement capital A happens to be sitting in what you would call the first quadrant of the coordinate system. Understand what I'm saying? But where it's sitting is, as far as its components are concerned, completely immaterial. What matters is how long is it and what direction does it point. So you know what I'm going to do? I'm going to redraw that displacement A with its tail at the origin. I think that's the safest way to deal with vectors. Okay? So let's draw our coordinate system. Make sure to label the X and Y axes. And now we should be able to draw the displacement A. All you got to do is redraw that arrow that you're given, but put its tail at the origin. So what quadrant of the coordinate system does it point into? Two, right? It starts here and it goes up like that, basically. A arrow. Everybody see that? I just redrew. The displacement is drawn in there, but put the tail at the origin. Okay, everybody take 5 seconds, shouldn't take any more than that, and sketch the two components. Make the triangle for me for that capital A arrow vector. Did you do it? Did you put little arrowheads on your components? You must, you must, you must. Watch out for that. Okay, let's start here. Let's do the X component first. Clearly the displacement points to the left and up, right? Let's drop a perpendicular here to the x-axis. Go straight over like that with a regular arrow. Look how you would label it. Capital A sub X. And then go up this way with a regular arrow. Look how it points and look how you label it. Capital A sub Y. That's how I would highly, highly, highly recommend you draw it. And don't drop anything that I've got there. Because any of those things dropped and you're likely to make a mistake later on. All right. So there's our sketch. Everybody understand? Let's tabulate what we know. I contend, although the problem is being a little bit sneaky and not telling me outright, I contend we have enough information to give you expressions for A sub X and A sub Y, the X and Y components. Remember, my answer for part A can be in terms of this edge length L. L is the length of either side of one of those squares. This picture might help you. What can you tell me about AX? Can you tell me what it is in terms of L? Yeah. 2L is part of it. And maybe I didn't hear everything you said, but there's another thing that has to be said. What's that? I have a hard time hearing folks because I got one thing in my ear here, so I've only got one ear going. Don't need to know a number, right? It's a symbol. We're going to get used to working with symbols, okay? You're going to have lots of pictures like this where you have to look at a picture and infer some information, okay? Yeah. Multiply by what? I still can't hear. You could do that kind of thing. Then you get what's called a vector component. And I know that was part of the video lecture, but right now I just want the scalar components. Yeah. Minus. Everybody see that? You must write this, negative 2L. Do you see that? It's absolutely vital that you see that. Any doubt about that? That's why you need to draw the arrow on the, see that little arrow pointing to the left? The left is negative X direction, isn't it? The diagram is telling you, watch out, this X component of A is a negative quantity. And to not write the negative sign means you have it half wrong. And the most you could get is half the points on that particular little question. All right, tell me what you can about a sub y. You might have to look carefully at the pictures. Yeah. Plus 3L, right? Because for this, you go 1, 2, 3 grid spaces, 3 squares. And it's in the positive direction, right? Look at the a sub y now. So plus 3L. Now you've got the x and y scalar components of the vector that was called A. Okay, go across here, 1, 2 to the left, that's the x component. Now go up this way, 1, 2, 3. Right? 1, 2, 3. You're going from C4 to C7. Yes, that's 3 steps. Okay, so 3L. All right, does everybody see that? Note, you had to figure those out for yourself, didn't you? It didn't just say outright, oh, here's a vector with an x scalar component of negative 2L and a y scalar component of positive 3L. No, it's telling us in a roundabout way. Now we can actually answer part A. Part A asks, what is the magnitude of this vector, right? On an arrow like that for a vector, what is magnitude? What part of the arrow is that? Oh, no? No, just asking you what the word magnitude means. Length. How long is that arrow? How long is that arrow right there? Okay? Here's how I denote magnitude of a vector. I draw the symbol for the vector, and I put absolute value sign. I'm trying to be very clear to my audience. Only want the magnitude, please. Anybody tell me how to get that magnitude? Here's what I do know, these two things. Yeah. Yeah. Whose theorem are you using? Pythagoras. Let's give some honor to the ancient Greeks. Square root of ax squared plus ay squared. Right? Right triangle. I've got 2 of the legs. I got the 2 legs. I need the hypotenuse, the length of it. Now plug in what you know about ax and ay. Ax is negative 2L quantity squared plus ay is 3L quantity squared, right? Or negative 2L squared is 4L squared, and 3L squared is 9L squared. All right? Be careful. Square root of something like little a plus little b is not the square root of little a plus the square root of little b. Don't do that. All right? Your algebra teacher would have a fit. Just add them inside the square root, yes? 4L squared plus 9L squared is 13L squared. Now you can take the square root of the L squared part if you want. You've got square root of 13 times the L out this back where I've taken the square root of the L. So you just go to your calculator if you want a decimal approximation to 3 sig figs. I get 3.61, that's the square root of 13 to 3 sig figs, 3.61 times L. And please, you always want to mark your answer clearly. Okay? We have found the magnitude of the displacement here. Now part B. Direction. Directions can get tricky because we all have to be on the same page, so to speak, as to how we're going to communicate direction for a vector. And our book has a specific way it does it, and that's the way I'm going to do it, so that's the way I want you to do it. Here we are told to find the direction, we'll call it theta, of this displacement, and the angle theta has got to be measured from the plus x axis. All right, I'll draw it over here, redraw my picture, x and y. There's a arrow, there's a sub x and a sub y. Do you see where the theta would be drawn? You see how you would draw the theta in that picture? You got to start at plus x and go around until you hit A. If I go the shortest distance, I would be inclined to go this way. And I'm going to put a little arrowhead to show which way I'm going around. Right? That's theta. That's what I'm supposed to find. Here's what you got to remember. It's in one of our video lectures, and it's in the book. If we're going to measure angles from plus x. If you go counterclockwise to measure your angle, note that's the way this one goes. Counterclockwise means against the way the clock hand points. Old-fashioned clock hand like that. Okay, hands. The angle is positive. But if you go around clockwise from the plus x direction, that would be going this way. It's a negative angle. But I went counterclockwise. Everybody see that? So my angle here for theta is going to have to be a positive number, and I'm going to give you the answer in degrees. And I know it's going to be positive, so I can put that right there. And I have to get that. Another reason direction is subtle. You're working with what's called an inverse trig function on your calculator. I'll show you why I'm worried about that. I'm going to find that theta kind of indirectly. Here's what I'm going to find. Just the size of that acute angle right down there in the lower right of the component triangle. Let me label it something. Don't label it theta, for heaven's sakes. That theta has already been taken. Let's call that's the Greek letter phi. I'm going to find that phi. Can I get the theta then once I have the phi? Yes. I always work with the component triangle first. That's just one of the acute angles in the component triangle. Let's just use trig to get phi. Let's use the fact that we know AX and AY. Okay, let's use that information. Can you tell me how to get the angle phi using AX and AY? Tangent, yes? The tangent of an angle is opposite over adjacent. So tan phi is, look at the right triangle, the side opposite is AY, and divide by the side adjacent, AX. You got to look at your triangle and see it opposite and adjacent. So phi is going to be what's called the inverse tangent, tan to the -1. That just stands for inverse tangent of AY over AX. But here's another reason angles are subtle. I just want the size of that phi. Are you with me? Just how big is it in degrees? And I definitely don't want a negative value for it. That's only going to confuse me. I just want to know how big that angle phi is. So actually, I'm going to take the absolute value of that ratio, AY over AX. Because if you don't, in this case, your calculator is going to give you a negative answer. And that's just going to confuse you. Because that's the way it's programmed. So we're taking the inverse tangent. If I do absolute values, that's 3L over 2L. And the L's cancel, hence you don't need to know L. And you're just taking the inverse tangent of 1.5. And if your calculator's in degree mode, it will tell you that that is 56.3 degrees. Okay, 56.3 degrees. And that's just how big this acute angle is that I've labeled phi. And you can check it if you want. If you take the inverse tangent of negative 1.5, it'll say negative 56.3 degrees. That's what your calculator will say. I'll say more about that in just a second. But let's get our theta. You see how to get theta? That's the actual answer. How do I get theta now?
You subtract 180.
Okay, Salim said, do a subtraction from 180. Right? Theta plus phi is 180 degrees. So theta is 180 degrees minus the phi, 56.3. And that turns out to be 123.7. If I round it to 3 sig figs, 124 degrees. Everybody understand how I got that? That's what you would have to enter in Wiley plus. Okay? Why would it be wrong to give either 56.3 or negative 56.3?
Negative, oh, 6.3 would be not giving you the angle you're asking for, because you're asking for the plus x-axis. Negative 6.3 would be from the plus x-axis plus down.
Down. Negative 56.3 would be for a vector pointing exactly opposite to this A. Exactly opposite. So if you enter negative 56.3, you've got the direction exactly reversed. And 56.3, just without the negative, would put it right here, wouldn't it? In the first quadrant. But it's not. It's in the second quadrant. Okay? So watch out. When you enter directions of vectors in Wiley plus, read it carefully and make sure you're giving them the angle they want you to give. Okay? Okay. So that's an example of a standard Wiley plus type problem where we do some practicing with vectors. Let's continue practicing with vectors. Okay, got 15 minutes. We're going to talk now about adding vectors by components and a little bit, either today or Wednesday, about what are called unit vectors. The key thing here is that we have to be able to add and subtract vectors in magnitude angle notation and in unit vector notation. I call it by components, so I want to practice with that. Okay, I'm going to clear this board here because we're going to draw some more pictures. Here's the scenario. You are to make 4 straight line moves on a flat desert floor, starting at the origin of an XY coordinate system and ending up at these X and Y coordinates. This is where you end up after the 4 moves. X is negative 140 meters and Y is positive 30 meters. Okay? But so you go from the origin to this location. Everybody understand that? In 4 moves. 4 distinct displacements. They're going to tell me some information about those 4 displacements. All right, one by one. The X and Y component of your moves are the following respectively in meters. This is just one way to try to tell you the scalar components of the individual displacements. They're all in meters. The first displacement has an X component of 20 meters and a Y component of 60. I'm going to call that displacement, that's a vector, little a. Okay? That's just the notation I'm going to use. Here's what they're going to tell me about the second move, the second displacement. Its X component is unknown, so they're going to label it BX. And its Y component is negative 70 meters. So I'm going to call that displacement little b. The third displacement is going to be labeled little c. Its X component is negative 20 meters, and I don't know its Y component. They're just telling me the symbol. It has some y component, c sub y. And here are the components of the fourth displacement. The x component is negative 60 meters. The y component is negative 70 meters. We are to find a number of things, like the component bx that they didn't tell me, and the component cy that they didn't tell me, and the magnitude and direction of the net displacement. Okay, so this is one of those problems where a sketch is going to make all the difference between being able to solve it and not being able to solve it. Okay? Because there is no picture provided whatsoever. We have to come up with it all ourselves based on the wording. So let's imagine we're looking down from above on this desert floor, flat desert floor, and the x-axis in meters and the y-axis in meters. And I found it convenient, just for making some sketches, to put on some tick marks going out. Each tick mark is going to represent 50 meters on both axes, okay? Like so. Note where we start, right? We start at the origin. Let's figure out where we finish. Well, we're told the coordinates of where we finish. Negative 140 meters, comma, 30 meters, or negative 140 meters and 30 meters. Right? So they're telling me the x component, or the x coordinate, and the y coordinate. We've got a grid here. We can estimate 140 meters in the negative x direction. If each tick mark is 50, that's roughly here. And then 30 in the plus y. So it's roughly right about there. You see what I'm saying? It's just a sketch. So that's the finish. That's where you end up, folks, right there. Let's just draw that, what they call the net displacement, total displacement for all this traveling. Well, you started there and you ended there, yes? So your total displacement vector would be like that. Where did you start? Where did you finish? Okay. I better label it something. This arrow, I labeled it R arrow, net displacement. Okay. That's an important part of this little practice. Now remember, there are 4 separate displacements that get us from the origin to the finish point, right? 4 separate moves. I'll draw the first one A because I know enough information to do it. Remember my first displacement I called little a? There's its x component, plus 20 meters, and there's its y component, plus 60. And the first displacement, well, you had to be at the starting point to begin with, right? So you start at the origin, and you go 20 meters to the right and 60 meters up. Just sketch it. So roughly there to there. And I label it little a arrow, just so you can see the first one. See what I'm saying? But then there's little b, and then little c, and then little d. 3 more displacements. I can't even draw b and c, right? Because I don't know yet their x or y component respectively. I could draw d, except I would tend to draw d at the head of c, and I haven't drawn that one yet. So I'm not going to draw anything more at this point. But at least I've got 2 of the vectors. But if I call the individual displacements little a, little b, little c, and little d, tell me how little a, little b, little c, and little d are related to little r. You add them up, right? Little r is the net displacement. Net means total, right? So what we know is that little r arrow equals little a arrow plus little b arrow plus little c arrow plus little d arrow. Vector addition, multiple vectors. And when I said this is about adding vectors by components, Here's the key thing. The way you add vectors by components is you add the x and y components separately. It's that simple. So this is really, in our case, for this two-dimensional situation, two equations. It's a very compact way of writing two equations. One for x components and another equation for y components. So here's how I would write it by components. R sub x, the x component of the net displacement, equals a sub x plus b sub x plus c sub x plus d sub x. Right? That's how you get the x component of the sum. Add the x components of the individual vectors. And then I'll put a comma here to separate. There is a separate equation for y components. The y component of the net displacement, r sub y, is a sub y plus b sub y plus c sub y plus d sub y. This is the way you add vectors by components. I mean, it is literally add the x components and then separately add the y components. And don't ever mix x and y. Okay? That's all you got to do. So, can you tell me how I'm going to answer part A? I am to find this unknown x component for the second displacement. That component that we've labeled b sub x. Yeah.
Plug in your x values and you do this algebra to solve for b sub x.
So you're telling me that I go to my x formula. So you're telling me to focus on this line right here. And you're telling me to plug in the numbers for all the x components that I know and solve for b sub x. I agree. In fact, let's do the vector algebra and solve for b sub x and then plug in the numbers. All right? Algebra first. These follow the rules of algebra, just like you learned in 9th grade. No, no, K-N-O-W, meaning I know. I know, I know, I know, I know, I don't know. So just solve for that, all right? Isolate it. B sub x equals, you got to be able to do the algebra right, r sub x minus a sub x minus c sub x minus d sub x. And now plug in the x components one by one into that expression and be meticulous about positive and negative signs. Because unfortunately, Wiley Plus and nature will accept not even one mistake, right? Okay, what's r sub x? Because that's going to go in my first set of parentheses here, r sub x. Negative 140 meters, right? There's r sub x. Then minus a sub x. What's that? Anybody? 20 meters. So minus 20 meters. Minus c sub x. What's that? What's that? Negative 20 meters. You cannot drop that negative sign. Minus d sub x. What's that? Negative 60 meters. Everybody see that? You must be brutally consistent with your signs. But it'll always work correctly if you are. And you put that in your calculator, okay? And you get negative 80 meters. That's b sub x. That second displacement has a pretty large negative x component. That's the number that goes here. Okay? Next, it asks me for the y component of the third displacement, the thing we're calling cy. You see how we're going to do it? It's asking for a y component, right? So use the y component equation. And the good news is you know everything in it except c sub y. So you solve algebraically for c sub y. R sub y minus a sub y minus b sub y minus d sub y. Must be able to do that algebra correctly. And then plug in the numbers one by one for these y components, and they all have to be with the correct sign. What's r sub y? 30. 30 meters minus, next comes a sub y. What's that? 60 meters minus, next comes b sub y. What's that? Negative 70 meters, and then minus, and last comes d sub y. Another negative 70 meters. Every sign must be correct. And you put that in your calculator and you get positive 110 meters. So that tells me the y component of the third displacement is quite large and positive. Everybody see that? Standard practice with adding vectors by components. Now let me just mention, because to be honest with you, you ought to be able to do C and D on your own. C asks, what's the magnitude of the net displacement? What's the direction of the net displacement measured relative to plus x? You see what we're in part C? Do you see what we're asking for? In this picture, what is part C asking for? What part of it? The length of it, right? Magnitude means length. So part C is asking only for the length of that arrow. How would you get it? I've got the two components of it, don't I? There's the x component, there's the y component. Pythagoras, yes? You get 143 meters if you want to try it. Check yourself. D, the angle measured relative to plus x. Should be able to draw it on the diagram. Okay, here's how I would draw it. Measured relative to plus x, I'm going to go around counterclockwise until I hit the r vector, and even put a little arrow on it to show you which way I rotated. That's going around counterclockwise, yes? So I'm going to find that angle theta. Is it going to be positive or negative? Positive, because the convention is a counterclockwise angle is positive. But you know what I would do? First, I would find that angle right there, maybe call it phi. You see what I'm talking about? Like I just did on that example problem. And I'll tell you that the phi is 12.1 degrees. Little inverse tangent will do it for you. So the theta is 180 degrees minus the phi. And that turns out to be 168 degrees. Okay? Okay, first thing on Wednesday, I'll do one more. Vector addition by components. Okay? And then we're going to start chapter 4.
Thank you.
You're welcome.